Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 5 of a little mini-series within that playlist that I'm calling Repeated Measures One-Way Fixed Effects ANOVA. And here we're going to look at the distributional properties of the sum of squares. Now in part 4 we derive the sum of squares for a reference. Now as a reminder, the model is y equals x beta plus air, and then we partition the design matrix into a column of ones, x tau and x beta, and then these are the beta parameters associated with the n subjects. The taus are associated with the A treatment effects, and this is a grand mean. Beta and epsilon are normally distributed with constant variances. Beta and epsilon are independent. So let's find the mean of y, the invariance. So the mean of y. Now if we plug in what we know about y, we get this, and so the expected value is a linear operator, so it goes in, and the only random variables are beta and epsilon, and these are 0, so we're left with mu 1 and tau, x tau times tau. Now the variance associated with y, these are constants, so they don't factor into the variance, so we're looking at this variance. So it's the sum of these variances. But here, the x beta comes out front and it goes out back transpose. That's what this is. And I have a video on random vectors and matrices if you want to see this in detail. We go in very great detail in how to derive this. It's random vectors and random matrices. The variance of epsilon. So here the variance of beta is sigma beta squared I. So the sigma squared comes out and the I kind of goes away, and here it's sigma squared I. So this is the variance. Now in the previous video we also derived the form of this, which is block. It's a block matrix, and each block has the identity matrix repeated over and over. Now some of these properties that we're covering we're going to need on the bottom of page 3. And that if we look at m tau, so this is the perpendicular projection matrix on the column space of x tau, and we're going to multiply it times x beta and x beta prime, or transpose. So this here is a block matrix of identity matrix, and m tau is a block diagonal with 1 over n constant everywhere. So U is a matrix of all ones. And then when we multiply this out, we get a block matrix of 1 over n un. But if every block contains 1 over n, that means the whole matrix contains 1 over n. So we'll just call it 1 over n una. Now if we multiply this times 1, a divided by a, then na UNA is actually J. It's the perpendicular projection matrix on the column space of ones. Now here J times x beta prime. J is this. Again, this is a block matrix of identity matrices. We multiply this out and we get because we're adding it up, we get A of them, and then the n over A stays the same, and then this carries along. Anyway, you're just going to have to multiply that out. I didn't do a good job of explaining it, but the A's cancel, or they don't cancel. This NA times mu is J, so we get that back. Now here, J times x tau is this, and then if we take like this first row times this, we're going to get n, and then the next row times this, we're going to get n. And so essentially we get n times a matrix of all ones, right? Normally it'd be a matrix of n's, but if we factor out an n, then it's a matrix of ones times n. Now the n's cancel and we're left with 1 over a una. Now if we were to multiply by n, divide by n, this could be j, so it's n times j. Now here, the perpendicular projection matrix onto the column space, or times x tau. Now remember, x tau is in the column space of x tau, and m tau projects everything down into the column space, so we get it back. That's the property of a perpendicular projection matrix. Now here, the format of x tau times this tau vector, it picks off the 1 and then picks off the 1, and so we get tau 1 n times, and then we get tau 2 n times, and then all the way to tau a n times. And the last property, these are a little bit detailed, but we need them when we're looking at the non-centrality parameter of the chi-square distribution. Property 6 is j times x tau tau. Now think about this. This is a vector, and we pre-multiply by j. And j is a perpendicular projection matrix on the column space of 1s, so this is going to shove it onto a constant vector. So that better be the result. And then this here, jx tau, we said was this. And then remember, this is a matrix of all 1s. It has a columns and NA rows. So there, we take the sum, but then we're dividing by a, take the sum, divide by a, take the sum. So it's actually the grand mean of the taus times the 1 vector. So now let's jump right into the expected values of these sum of squares. And I'm going to pass you off to a video that I have titled Mean Variance Covariance of Quadratic Forms. And in there we derive the formulas that we're going to use in this video. So the expected value of the sum squared error, we put its quadratic form in, and that's because then we're going to make use of this video here, and it ends up being the trace of this center matrix times the variance of y plus the expected value of y, transpose, times that matrix times the expected value of y. Now, here, so we put in the variance of y, which we derived up there as this, and then the expected value of y is this, and we need a transpose there. I minus m, and then the expected value of y. Now, this piece, let's look at it first. So I minus m is a perpendicular projection matrix that projects it into NA space, but perpendicular to the column space of x. And so since x beta is in the column space of x, I minus m times x is 0. So this is 0. And if you want to go through those properties that we just did, that'll also help. You can kind of do it, at each step. I minus m times this, you just get I minus m back. So this piece goes here. Now over here, remember this is a perpendicular projection matrix onto n space, but perpendicular to column space of x. Now the 1 vector is in the column space of x, so this times that is 0. X tau is in the column space of x, so this times that is 0. So this goes away, and that's why we're only left with this. Now the trace, the sigma squared come out front, I, and m is m tau plus m beta minus j, so we get this. And then the trace of each of those, we get NA, A, N, and 1. Oop, where's my 1? And then this is this product. And actually, so we can find an unbiased estimate for sigma squared is if we take this and divide it to the other side, and which is the mean squared error. It's actually an unbiased estimate for sigma squared. So now let's look at the expected value of the sum of squares treatment, which in quadratic form is this. So it's the trace of this matrix minus, or times the variance, which is this, plus the mean of y, times that matrix, mean of y. Now here, when you do we did the properties of m tau beta and j beta, and we got the same thing, A times J and A times J. So this piece goes to 0, and then that multiplied in is this. Now over here, this is a perpendicular projection matrix onto the column space of x tau, but orthogonal to the 1 vector. So this is in the column space of tau, but it has to be orthogonal to the 1 vector. So this times this is 0. Same way from over here. Now over here, remember this, this times, so the x tau comes in, that's x tau, and then this is j, and that's from the properties. So this times that, we get this, right? So if we just think about taking the x times each of those, we get this, and the tau's left out. Now, since this is idempotent, we can take it times itself and use one of those here and one of those over here, and that's why we get this transpose. Now, x tau times tau is, it's 1 times this n vector, and this is the grand mean for x tau. And then we get this structure. But then the two vectors is the same, so that vector product, we get this. So this is going to be the non-centrality parameter. And actually, so that means under the null hypothesis of no treatment effect, then the non-centrality parameter is going to be 0. Because if there's no treatment effect, then these are all the same, which equals the mean of those taus. Now the distribution of the sum of squares. So we found the mean or expected values of sum of squares. Now for the distribution, I need to pass you off to a video called Distribution of Quadratic Forms. And in there we derive how to find these distributions. Now in the first part, we found the mean of y and the variance of y, and it's multivariate normal. But here we need to find the distribution of y divided by sigma, and it's really, so the mean is just, you have to divide by sigma, so it's the mean of y divided by sigma, so that's what these are, and then you have to factor out a sigma squared. Normally there'd be a sigma squared here, but this, when it goes in, cancels it, but we get a sigma squared here. So this is the mean of this distribution. And so to use this formula, we need to find the mean. So we're going to try to find the sum of squared error, the distribution. And this is the matrix in the middle. That's what this is. And this is the variance. So this matrix times the variance, covariance matrix, has to be idempotent for us to use this theory. So we have to take this distribution and see if it's idempotent. So I minus m is a perpendicular projection matrix into NA space, but perpendicular column space of x. So since this is in the column space of x, this times that is 0, so it goes away. And then this times this, we just get this times this, which is I minus m. But I minus m is idempotent, so this part of the theorem is true. And then we also need the rank of I minus m, which we found to be a minus 1 times n minus 1. So that tells me, now, that remember this y is actually y over sigma, and this is y over sigma. But we combine the sigmas to be sigma squared. So this distribution, according to the theorems in here, it's a non-central chi-square distribution with degrees of freedom equal to the rank of this matrix, and the non-centrality parameter is the mean of y times that matrix, I minus m, times the mean of y. Now this we showed was 0, so this is a perpendicular projection matrix on into Rn space, but orthogonal to x. Since 1 lives in x, this times that 0, and since x tau lives in x, I minus m times that creates a 0 matrix. So this is a central chi-squared with a minus 1 times n minus 1 degrees of freedom. So it's unconditionally a central chi-square distribution. Now the sum of squares treatment, we need to show, so the sum of squares treatment is y, m tau minus jy. So we need to show that this matrix times the variance is idempotent. So this times this, we get 0, like similar to an argument we used up there. And then this times I, you just get it back. And m tau minus j is idempotent. So that part of the theorem holds. And so to use the theorem, it's a non-central chi-squared with degrees of freedom equal to the rank of this, which is a minus 1. And then it's the mean of y, which we said was here, times this matrix, times the mean of y. This comes down. Now, when we calculated the expected value, we derived this to be this. I'm not going to go through that again, but we did it right here. Okay, so that says under the null hypothesis, it's a central chi-squared with a minus 1 degrees of freedom. Under the alternative, it's a non-central chi-squared, which then this is a quadratic form, and this is idempotent. That means it's positive semi-definite, so it's always positive, well, except for under the null. So that's going to shove that value to the right into the tail, which of course creates a small p-value. Now, the independence of sum squared error and sum squared treatment is if the product of those matrices is equal to 0. So we take this times that and this times that. Now this is a perpendicular projection matrix onto NA space orthogonal to the X column space of X. And both of these live in the column space of X, so this has to be 0. So now to create an Ftest statistic, we take this chi-squared divided by its degrees of freedom, this chi-squared divided by its degrees of freedom, and this is the general form. Now this is a non-central chi-squared in general. Under the null, it's a central. But in general, it's going to be a non-central F distribution with numerator degrees of freedom, denominator degrees of freedom, and then this non-centrality parameter, which is derived from the non-centrality parameter of that chi-square distribution. So now if the null hypothesis is true, that there's no treatment effect, and this is for all I, then it becomes a central F distribution, right? And the hypothesis is that there's no treatment effect, meaning every treatment effect's equal to the mean. It's a constant value, or one of them is different from the overall mean. So there is some sort of treatment effect. Now note the subject effect is generally not of interest, and so we're not even going to think about that. Now, if you do a paired t-test, you don't do a test to see if there's a subject difference. You only do a test if there's a treatment difference. It's the same thing here. So the fitted values for our model is my, right? This is like the hat matrix in multiple linear regression. You pre-multiply y by it and you put a hat on y. But m is, m tau plus m beta plus j, and we derived that in a previous video. And then when you take y into each of those, you create this mean vector. The treatment mean plus the between subject mean, or the subject mean or the block mean minus the grand mean. See part 2 for more details. So this is a matrix form. In scalar form, yij hat is yi dot bar. So it's the ith treatment mean plus the jth subject mean minus the grand mean. Now the residual is E, so it's y minus the fitted value. But the fitted value is my, so then you can factor out of y, and it's I minus m. So these are the residuals for our model. And in scalar form, it's Eij is equal to Yij, so it's the data value minus the fit. So it's the treatment mean minus the subject mean, and then plus the grand mean. Okay, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Now the next video deals with treatment contrast in this repeated measures one-way fixed effects ANOVA. And it's pretty exciting that how it all works out. And that's the next video. So please like the video and subscribe so you don't miss the next one. Thanks, bye.